Good morning, everyone.
Morning.
So in the previous meeting of the calculus forum, we had discussed about the discontinuities of a function. So shall we have a detailed discussion on it today?
Yeah, we had a long and continuous discussion on some good problems the other day. We needed a break. Now today we shall do some discussion on discontinuities of a function.
Okay.
Let me start today's conversation with the following question. So let f be a continuous function on the closed interval AB with values in R. The question is, do you have a subset A of the closed interval AB such that if you know the values of fx for x in A, the function f is completely determined.
Sir, can you explain the problem once more? We do not understand.
I will try to put it in a different way.
Okay.
Suppose you know the values of this function at say some points fx1, fx2, etc. up to let us say fx10, where these points x1, x2, x10 are in AB. Then from this information, can you determine the continuous function f completely?
Yes, certainly we can. We can find a continuous function f that agrees with its values at these points xi.
But how do you say that?
So let me show it here. Just need to join the points xi, comma f of xi by straight lines. So suppose this is x1, x2, etc., xn, x10, and I have some value, the value of the function at these points is something like this, then I just need to join these points by straight lines.
Okay.
Yeah. Then we'll have a continuous function whose values agree at these points.
Yeah, how many such continuous functions are there?
Oh, I think in this case there will be infinitely many functions, because instead of taking this straight line arc, we can take any curved arc, and for each such thing we will get we just have to join these pair points by a arc.
Yeah.
So that can be taken any curve. So there will be infinitely many such functions that will be agreeing with this function at these points.
Yeah.
Good. See, we see that if you know the values of a continuous function on a finite subset, the function is not completely determined. You can have infinitely many solutions. So let me change the question now. Okay? With the same assumptions as before, say f is a continuous function from a, b to r. Now the question is, can you find a subset, say a proper subset S of AB, so that the function f is completely determined by its values on S. In other words, if you know what is f of x for x in S, f of y for any y in AB can be determined.
Yeah, I can try. Take your SS open interval AB. Then, and for if it is given that f from closed interval AB to R, it is continuous. So we must have f of A equal to limit x tends to A plus f of x, and f of B equal to limit x tends to B minus f of x. So if we define f of A equal to right hand limit of f as x tends to A from the right hand side, and f of B equal to left hand limit of f as x tends to B from left hand side, then we are done.
Yeah.
Yeah, in fact, for the same reason, we can define f, we can actually take a finite set S to be the closed interval AB minus a finite set of points x1, etc., xn, and such that f of xi is limit as x tends to xi, f of x. Yeah.
Yeah.
So again, since the right hand side depends only on the values of x in a neighborhood of xi, that's fine. We can define it in such a way, and this set S will serve the purpose.
Good, you are right. But this subset S that you have taken is almost as big as the whole interval AB.
Yeah.
So, can you think of a smaller subset?
Yes, sir, I can try. See, for any point x0 belongs to closed interval AB, we have f of x0 equal to limit x tends to x0 f of x. And also for limit x tends to x0 f of x equal to L, this is if and only if limit n tending to infinity f of Pn equal to L for every sequence Pn in AB, okay, and Pn converts to x0.
Yeah.
Okay,
Yeah.
this is true. So our job is to find a subset S of AB such that every point in AB will be limit of such sequence that is coming from S.
Yeah.
So I am looking for such subset S.
Yeah. So you mean the closure of S?
Yes, yes. I think in that case, that S subset should be such that it will be a dense subset of AB.
Oh, that means we can take subset S of AB as set of rational numbers in AB. That means because it is dense in AB.
Yeah.
So we can take S equal to Q intersection closed interval AB. Now in this case, if we know the values of F on S, then we can determine F completely on closed interval AB because it is given to be continuous function.
Yeah.
So in general we can say that if we have given a continuous function on a dense set, then we can determine that continuous function everywhere.
Yeah.
So also more we can say about this thing. See, if you have given a continuous function and a dense set, and this continuous function is uniquely determined on this dense set. Suppose if you have two continuous functions f and g, and that agree the same value on this dense set, then that will agree on everywhere.
Yeah. So two continuous functions, if they agree on a dense subset, then they agree everywhere.
Yes, yes, you are
Yeah.
correct.
Yeah, you looked at the set of rationals in AB, isn't it? There are several other dense subsets. Where did you choose the rationals?
Oh, I think even the irrational will also work.
Yeah.
Yeah, but you should remember that we were looking for a small subset of AB, as small as possible. So any dense set, but if a set is not dense, it won't work. And we have already seen that a finite set doesn't work. So the next bigger set is a countable infinite. Rationals are countable, and then say the set of rationals in AB. See, that dense subset works. See, I'm going to look at the same problem from a different angle now. Not the same problem, but I'm going to look at this problem of continuity and discontinuity from a different angle. So for example, I have a function, right? I have a function defined on an interval AB, and x0 is an interior point, and in neighborhood of x0, the function is continuous, right? See, it is continuous except at x0. Okay, so can you redefine, can you alter or change the value of fx0 and make f continuous at x0?
Yes. So what we have is f is continuous at x0 if and only if limit as x tends to x0 f of x is equal to f of x0. So if it is not continuous, then either this limit is not equal to f of x0, that is f is discontinuous at x0. If this is true, then either limit as x tends to x0 f of x is not equal to f of x0, or the limit does not exist, that is the limit as x tends to x0 f of x does not exist.
Yes.
Yeah. Okay, let me analyze the first.
Okay.
See, in first case, limit exists and limiting value is not equal to f of f at x0. Suppose L equal to limit x tends to x0 f of x, and this L is not equal to f of x0. Okay.
Yeah.
Now I want to redefine this function f so that it will be continuous at x0.
Yes.
So suppose capital F of x equal to small f of x if x not equal to x0.
Yeah.
Okay.
Okay.
And it is equal to L if x equal to x0. Then we can see that easily this capital F of x, capital F is continuous at x0.
Yeah.
Okay. And also limit x tends to x0 f of x equal to L.
Yeah.
That is if and only limit x tends to x0 plus f of x equal to L equal to limit x tends to x0 minus f of x.
Yeah. So such a point of discontinuity is called a removable discontinuity. So can you think of an example?
Oh, I know that sin x by x would be an example of such a function.
Yeah. Where is the removable discontinuity?
It is at 0.
But the function sin x over x is not even defined at 0. So maybe in that sense it's not such a good example. Can you think of something else, some other example?
Yes, sir. I can give you another example. See, suppose f is a function from R to R, and f is defined by f of x equal to x square minus 3x plus 2 divisible by x minus 1 if x is not equal to 1, and it is equal to 0 if x equal to 1.
Okay.
Now we can see that limit x tends to 1 f of x equal to limit x tends to 1 x square minus 3x plus 2 divisible by x minus 1. Okay. And that is nothing but limit x tends to 1 x minus 2 into x minus 1 divisible by x minus 1.
Yeah.
And that is nothing but limit x tends to 1 x minus 2.
Yeah.
Okay. And that is nothing but minus 1. Right? So if we read, so clearly from here we can see that our limiting value at x equal to 1 we are getting minus 1, but whereas we have given that f of 1 equal to 0.
Yeah.
that means we have a discontinuity at the point x equal to 1.
Yeah.
Okay, so we can redefine a function, new function that is equal to capital X. Suppose capital F of x equal to x square minus 3x plus 2 divisible by x minus 1 if x not equal to 1,
Yeah.
right? And
And
minus 1
Yeah.
if x equal to 1.
Hmm.
Then f is clearly continuous at x equal to 1, and not only it is continuous on whole real line.
Yeah.
And this x equal to 1 is a removable
Point of
discontinuity at the point x equal to 1.
Yeah.
Right?
So I think now I can redefine my example. Say f of x is sin x by x when x is not equal 0, and say it is 0 at x equals 0. Then the 0 is a point of definition, and
Point of discontinuity.
it is in the domain also.
Yes.
And that limit extends to 0 f of x, that is limit extends to 0 sin x by x, which is 1. So we can redefine that capital F as sin x by x when x is not equal 0, and 1 when x is equal 0.
Yeah.
So this is also a point of removable discontinuity.
The simplest such example would be, why not this, right? I define f of x to be x over x when x is not equal to 0, and 0 when x equal to 0.
Yeah, that will also work.
Yeah. So this function again has a discontinuity at x is equal to 0, because limit as x tends to 0, f of x is equal to 1, and that is not equal to f of 0.
Yes.
So x is equal to 0 is a point of removable discontinuity. Yeah.
Now let us look at the various possibilities of
Okay.
discontinuity. Discontinuities. So first possibility is that both left hand limit of fx as x tends to a minus, and right hand limit of fx as x tends to a plus, both exist. Okay, and then in sub case of this we say that, let us say 1a both exists and equal. Okay, limit of x as x tends to a, and this is equal to limit of fx as right hand limit. And as you know, in this case we say that the limit exists, so we can as well call this as limit of fx as x tends to a, but this limit is not the same as the value of f at the point a, so not equal to f of a. And this is a case which we already discussed,
Yes.
and that is what is called removable discontinuity. Okay.
Yes.
Then the sub case of this, that is both the limits exist but they are not equal. Okay, that is limit fx as x tends to a minus is not equal to limit fx as x tends to a plus. Okay, and then this exhausts the two cases when both the limits exist. The second possibility is that one of these limits doesn't exist.
Yes.
Okay.
That is limit fx as x tends to a minus, or limit fx as x tends to a plus does not exist. The points of discontinuity are classified according to these various possibilities. The first case we have already discussed, removal discontinuity. So let us now just discuss the other two possibilities. If this happens, that means if both the left hand limit as well as the right hand limit exists, but if they are not equal, then that is called jump discontinuity.
Okay.
Jump discontinuity, or also discontinuity of the first kind.
Yes.
Of first kind. Okay, and the second case, if one of these limits doesn't exist, then this is called discontinuity of second kind.
Both the limits also might not exist.
Yeah, that is included. Okay,
Okay.
discontinuity of second kind. You may be knowing that there is what is called OR, exclusive or inclusive.
Okay.
Usually when in mathematics we use OR, it is included that both cannot exist.
Okay.
So, can we have some examples?
I'll give it. So the first one is removable discontinuity. We have already seen examples for that case. Now let me give for jump discontinuity. So we can take the function f of x is equal to box x, that is the integral part of x. The graph of this function is something like this. So from values 0 to 1, it takes the value 0. From 1 to 2, it is 1. From 2 to 3, it will be 2. So we can see that this function has a jump discontinuity at all the integers. In this case, we see that f of n minus is nothing but n minus 1 for all integers, and f of n plus is n. So in this case, at all the integers, this function has a jump discontinuity.
So even I can give an example of a removable discontinuity at countably many points.
Yeah.
You just write the function.
Okay.
Gx you just define. Gx to be x when x is an integer,
Okay.
and at all other point it is 0.
Okay.
So it will have a removable discontinuity at all the integer point except 0.
Yeah.
Because at any other integer point, that left limit and right limit both are 0, but the function value is non-zero because it will be non-zero integer.
Yeah. So for x, which is an integer other than 0, we'll have g
Removable
of
discontinuity.
x plus will be
0,
and
g of x minus is also 0.
yeah,
But
but
the function value is not 0.
yeah, g
So
of
we can redefine this function as identically 0 everywhere, and it is a removable discontinuity.
yeah. So I can give another example for discontinuity of the second kind. So we can define h from minus pi to pi to the real line such that h of x is equal to sine 1 by x when x is not equal to 0 and 0 when x is equal to 0. So from the plot of this function we can see that h of 0 plus and h of 0 minus do not exist.
Yeah. From the plot, how do you say that? How do you say that the limits are different?
Okay, can you give us some hint?
We may recall a property of this left hand or right hand limits. So suppose limit of this hx as x tends to, I think this point is 0. Suppose this limit is q. Okay. Then what should happen is that if you take any sequence Tn in this part of the interval, that is your interval is minus pi to pi, this is 0. Suppose you take this sequence Tn lying here, that is Tn in this 0 to pi, and converging to 0, then what should happen is that h of Tn should converge to, so this should imply that h of Tn converges to q. And it should happen for every sequence Tn lying in the interval 0 to pi which converges to 0, h of Tn should converge to q. Okay. Does this help?
This is the sequence criterion for continuity that we had discussed earlier. So if we find two sequences Sn and Tn such that both Sn and Tn converge to 0 and Sn and h of Tn converge to two different numbers, then we are done.
So I think in this case you can take that Tn to be 1 by n pi and Sn to be 1 by 4n plus 1 pi by 2.
Yeah.
Taking those two sequences,
Yeah, yeah.
you just see.
Yeah, I think I can try. So your Tn is 1 upon n pi, and that is greater than 0 clearly, and that is true for all n equal to 1, 2, dot, dot, dot. So this Tn converts to 0 as n tends to infinity. H of Tn equal to sine n pi, and that is equal to 0. Okay, therefore h of Tn converts to 0.
Yeah.
Now Kuntal has said that already to take Sn equal to 1 upon 4n plus 1 into pi by 2.
Yes.
That is also strictly greater than 0 for all n equal to 1, 2, 3, etc. So h of Sn gives me sine of 4n plus 1 into pi by 2, and that is equal to 1.
Yeah.
Therefore h of Sn converts to 1.
Yes.
So we are getting two sequences Tn and Sn in 0 to pi open interval, such that h of Tn converts to 0 and h of Sn converts to 1. That means what? H of 0 plus, that right hand limit
Does not
exist.
that doesn't exist.
Right.
Yeah.
In the same argument you can say
So,
that left hand also will not
Yeah. So that means what? See, if right hand limit doesn't exist, that means H has a discontinuity of second kind at the point 0.
Yes.
See, if you look at a plot, as you go near 0, you see that there is no neighborhood in which the function is monotonic. It goes up and down, up and down, up and down.
Yeah.
Do you see that?
Yeah.
Yeah, good. I mean, this raises a very natural question. Can a monotonic function have a discontinuity, or what type of discontinuities it can have?
Yeah, a monotonic function can have discontinuities. That's my favorite example, which is f of x is equal to box x. This function has, this is monotonic. We can see from the graph that it is monotonic. It is something like this. And this function has a discontinuity at all the integer points.
Yes, that will.
Yes, but what do you observe about the type of discontinuity of a monotonic function?
This is having only jump discontinuity. But I don't know whether that is the intrinsic property of monotonic function.
See, why don't you try to construct a function, a monotonic function, which has a discontinuity in the second kind. Try to construct.
Yeah, I can try. See, take your f r to r be a function, and which is monotonically increasing, and also f has discontinuity of second kind. Say at x equal to 0 point, it has discontinuity of second kind. So we have the following. Number 1, for x less than equal to y, this implies fx less than equal to f of y, because f is monotonically increasing function. So second condition is, so either f of 0 plus or f of 0 minus doesn't exist, or both do not exist, f of 0 minus f of 0 plus. Now consider x less than 0 and approach x from left hand side towards 0. Okay, I am considering a subset of set of real number as follows: s equal to f of x such that x less than 0. Then we can see that f of x is less than equal to f of 0 for all x belongs to, for all x less than 0. Yeah, we can see clearly.
Yeah, so
Because
function
for
is equal-
x less than 0, fx belongs to s. That is why fx less than equal to f of 0. That means s is a bounded subset bounded above by f of 0, and this is bounded subset of R. So that means we can now apply least upper bound property of R. So
Bounded
that
and non-empty.
okay.
Yeah, you say non-empty and bounded above. Non-empty.
Okay. So we are getting for x less than 0, fx less than equal to f of 0. So that means s is bounded above by f of 0, and also s is non-empty. Clear. So therefore, by least upper bound property of R, s has least upper bound in R. Correct? Suppose alpha is the least upper bound of s, that is supremum of s. Let alpha equal to supremum of s. Then alpha is less than equal to f of 0, because f of 0 and upper bound and alpha is the supreme. Now for any epsilon greater than 0, alpha minus, for any epsilon greater than 0, there exists y equal to minus delta belongs to R, such that alpha minus epsilon, that is less than f of y, and that is less than equal to alpha. Correct? Also, for z belongs to minus delta to 0, alpha minus epsilon, that is less than f of y, less than equal to f of z, and that is less than equal to alpha, and that is less than equal to f of g. That means we can see that f of 0 minus this exists and equal to alpha, and the alpha is nothing but supremum of f of x, such that x less than g. That means left hand limit f of 0 minus exists. So am I in the right track?
Yeah, you're right.
So similarly, we can say that f of 0 plus, is nothing but the infimum of the set f of x such that x is greater than 0. So we see that f of 0 plus also exists. So a monotonic increasing function cannot have a discontinuity of the second kind.
Even I think you can, all these arguments will hold for a decreasing function also. Some suprema infirm you have to switch.
Yeah. So
it cannot
a
have.
monotonic function cannot have a discontinuity of the second kind.
Yes, good.
So you observe that if a function has a continuity of discontinuity of the second kind, see, in no neighborhood it can be monotonic, because monotonic functions discontinuities are all of the first kind.
Yeah. Okay.
Good. It can also be shown that the set of discontinuities of a monotonic function must be countable.
Okay. So shall I try to prove this?
Yes.
Yeah.
Yes.
And a small observation before that. See, so what we saw for sin 1 over x is not something special for sin 1 over x.
Yeah.
This happens for
Any
function having a point to discontinuity of the second kind. Yeah.
So now I shall try to show that the number of discontinuities of a monotonic function is countable. Suppose f from a comma b to r is monotonic. So we just saw that it cannot have discontinuities of the second kind. So both the left hand limit and the right hand limit should exist for every point in the set a comma b. And since the function is monotonic, it cannot have removable singularities as well. So now let us consider the set E to be the set of all x in AB, such that f of x plus is not equal to f of x minus. Yeah, only in this case we will have a discontinuity for a monotonic function.
Yes.
So now we have to show that E is countable. Am I correct?
Yeah. Yes. Proceed.
I think I can give my
Okay.
hand some more. So we have to show that this A set is countable. Now, suppose E belongs to E. Okay. Then I can assume that f is increasing function, because if we prove it for increasing function, decreasing will also hold in a similar way. So assume this f is increasing. t is in E, so f of t minus will be certainly strictly less than f of t plus, because these limits are not equal.
Yeah.
Now, if I take two t, say t1 and t2 in E, and say t1 is less than t2, then we can observe that f of t1 minus will be strictly less than f of t1 plus, that might be that is less equal f of t2 minus, that is strictly less than f of t2 plus, because of the monotonic increasing property. So we can see that this interval f of t1 minus to f of t1 plus, I am taking the open interval, to this interval f of t2 minus to f of t2 plus, I am taking the open interval, so this open interval intersection must be empty.
Yeah.
So now for each of these t in E, I can choose a rational number in this f of t minus and f of t plus. So for each t in this set E, choose a qt. I can choose it by axiom of choice, and I will fix it at one unit qt. I am choosing from rational number, such that qt is in this set f of t minus to f of t plus.
Yes.
So now for each t I can map it to a rational number. So I have a 1-1 map from this set E to this rational number
Yeah, because the
via
intersection is
this
empty.
Q map.
Yes.
Via this Q map. So I have a 1-1 map, and hence it is a countable subset of, it is a subset of a countable set. It must be countable. Hence that set E has to be a countable subset.
Yeah.
Yeah. See, if f is monotonic, and if in addition we let us assume it's also differentiable, then we can say something more. Actually, suppose f is monotonically increasing, right? Then if you look at this ratio, f of x plus h minus f of x by h, right? If you look at this ratio, it is always greater than or equal to 0.
Yes.
Right? So what happens to the limit?
Yeah. That will be
What can you say about the limit? That's also
It will
greater than or
also be
equal to
identical.
0. So this says that, and this limit is nothing but the derivative. Right?
Yeah.
So if f is monotonic, increasing in an interval, and if it is differentiable, then its derivative is non-negative.
Okay.
Yes. But will the converse also be true? Like
Yeah, there are 2-3 assumptions. So why not one of you state the converse
Yeah,
first?
I can, let me state the converse one. Suppose f is a differentiable function.
why
in
don't
the-
you write?
Okay. F is a differentiable function in open interval AB, and also it is given and f dash x that is greater than equal to 0 for all x belongs to open interval AB. Now from here, can we conclude that f is monotonically increasing function in the open interval AB? This is the conclusion.
So, isn't it natural? Can't we just retrace the steps and prove this?
How you will show?
So here now we need to show, to prove that f is monotonically increasing. Now we have that the derivative is greater than or equal to 0. So we have limit as h tends to 0, f of x plus h minus f of x by h. This is greater than or equal to 0. Now when h tends to 0, we'll have h is greater than 0 or h is less than 0. When h is greater than 0, since this quotient is non-negative, we have f of x plus h minus f of x to be greater than or equal to 0. In this case, the function is increasing. And in the case when h is less than 0, we'll have, again, since this quotient has to be non-negative, we'll have f of x minus h minus f of x to be less than or equal to 0. Again, in this case, we have f is an increasing function, and hence we have proved that f is monotonically increasing.
Yeah, but there is a slight problem in this argument.
Oh.
From the fact that limit is bigger than or equal to 0, you have concluded that the values of the ratio are also bigger than or equal to 0.
Yeah.
That may not be correct.
Oh.
So we need to use some other technique, maybe Lagrange's mean value theorem.
Oh.
I think the problem is only for that 0 part, I guess. Because if it is positive, then this value will be.
Yes, but in this case, since the limit is 0, you cannot conclude that way. Right?
Yeah.
Okay, so let me try using the mean value theorem. So, so for x comma y in the open interval AB such that a less than x less than y less than b, by the mean value theorem, there exists a xi in the open interval x comma y such that f of y minus f of x is equal to y minus x into f dash of xi. Now we are given that the derivative is non-negative for all x in AB, so this term is greater than or equal to 0, and y minus x is again strictly greater than 0. This is strictly greater than 0. So we have f of y minus f of x is greater than or equal to 0. So we have seen this function is increasing.
Very good. Please come in.
Oh, there is some discussion going on here. I just came to meet Professor Kulkarni.
Oh yes, why don't you also join the discussion? We have been discussing about the discontinuities of a function, and as such we don't mind any number of discontinuities.
You mean these interruptions?
Oh yes. We can interrupt this discussion on discontinuities of function temporarily.
Okay.
And if you have any problem, you can pose it.
Yeah, I'm just coming from a class on discrete mathematics. So I shall give them some puzzle and let them try to crack that puzzle. Okay, the puzzle is as follows.
Okay.
You are asked to find an unknown natural number less than 1000.
Okay.
And you are allowed to answer yes or no.
Okay.
So the question is, how many questions do you think that you need to find out that unknown natural number?
Okay, I have come across this puzzle before.
Oh, okay.
I can do it within 10 questions and answers.
Yeah, why don't you try?
Only 10 questions?
Yeah.
Okay, then let me think of a number and then.
And I will count the numbers, how many questions he is asking.
Okay.
Okay, fine. Okay.
So I have thought of a number less than 1000.
Okay, let me start.
Okay.
So first number is it greater than or equal to 512?
Yes.
Okay. Second number is it greater than or equal to 768?
Yes.
2.
Okay. Is it greater than or equal to 896?
3.
No.
Is it greater than or equal to 832?
No.
4.
So, is it greater than or equal to 800?
No.
5.
Is it greater than or equal to 784?
No.
6.
Is it greater than or equal to 776?
Yes.
7.
Okay. Is it greater than or equal to 780?
No.
8. So you have asked already 8 questions.
Okay, 8 questions we have asked, 2 questions remaining. So next, is it greater than or equal to 778?
No.
9.
That means we have 2 possibilities remaining. So my next question will be, so is it 776?
No.
Oh, that means 1 possibility remaining. So your number is 777.
Oh.
How did you guess it?
Yeah, that's a very pretty good thing, and I can play with my brother also. But I provided I know the logic. So what is the logic behind?
Yeah, actually, Kuntal, each natural number less than 1000 is actually of the form ABC,
Yeah.
where A, B, C can take any of the digits 0, 1, 2, 3 up to 9
Yeah.
actually. So for finding ABC number that is less than 1000, our job is to find ABC digits. We have to ask several yes no questions and answers.
Okay.
Because each one of ABC can take 10 values. The first one, 10 1 9.
Okay.
Fine, these are very good observations. So, can you find the number of possible values that each digit can take so that there is reduction in the number of possible values that it takes?
Oh, I think we can change the base instead of expressing it in terms of base 10. We can express in terms of base 5. Then we will have only 5 choices: 0, 1, 2, 3, 4.
Yeah, so I've got an idea. The best possible thing that we can do is convert it to the binary base.
Yeah,
So to
that
base
will-
2. So each digit in the binary representation can be either a 0 or a 1.
Yeah, yeah,
So a number less than 1000 is less than 2 power 10 and hence in the binary representation of the number it will have at the most 10 digits.
Yeah.
In that way we can just ask at most 10 questions and get the answer.
Okay,
to
okay,
the-
okay. Now I got
Yeah.
the logic.
Oh, this explains the problem completely. Have you understood, Kuntal?
Yes,
Now you can play with all your friends also.
Yes,
Not only with your brother.
Yeah.
Yes,
Right?
yes.
Yeah.
What was that?
Oh, that's a message. Actually, I just switch on after a long time.
How many messages are you getting continuously?
Oh, actually, it was off for a long time, no? That's why.
So what is the trend of the messages that you receive in a day?
Oh, that exact I cannot say, but it's roughly like this. So when I get up and it almost 0, then it's slowly increases. After some 10, it start increasing more.
So 10
And-
a.m. you start receiving messages properly.
yeah.
Okay.
Then it is going up to some 4-5 p.m. It will increase.
Okay.
Then after 5 it start decreasing, and after 10 p.m. I almost receive no messages. So it
Okay.
is kind of this.
Okay, it's now 11 o'clock. Can you tell me in the last, say the next 10 minutes, how many messages are you likely to receive based on your observations?
Okay, so suppose I take today's observation, then if I try to plot the number I received, the number of message I received versus the time, then and if I take some say n observation, then it will be a polynomial of degree n minus 1. So roughly it will be like this. So find that function f. So and if I take this linear approximation, it will be f of t plus delta t. It will be approximately f of t plus delta t times f dash of t.
Yes.
So now we have to find f of 11, and in next 10 minutes, so it will 11 plus 1 by 6.
Oh,
will
is
be-
it 1 by 6 is because an hour contains 60,
Yeah, 60
minutes and
minutes.
for the next 10 minutes
you are considering. So it will be roughly at f of 11 plus 1 by 6 times f dash at 11.
Yeah.
How many messages you have received till 10:50 a.m.?
So 56 messages.
So many messages.
That's a lot.
Yeah.
And how many between 10:50 and 11 a.m.?
That I received some 12 messages.
Okay.
Okay, so during the last 10 minutes you have received 12 messages,
Yeah.
and your calculation, according to your calculation, it should be 13 messages, right?
Yeah, it is kind of 13 message. Yeah.
Yeah, so according to what you have written, it should, with that calculation, it should be 13 messages. Yeah.
Okay. Oh, good. So your linear approximation is good enough to predict number of messages that you receive in every 10 minutes.
Yes.
That's good.
Yes.
That's really good.
Oh, the message reminds me of my meeting at 11:30. So let's close this discussion here.
Yeah.
Okay, sir.
Okay, but before closing, can you summarize what we did today?
Yeah, I can summarize. So in today's discussion, we have learned several things about continuous functions, also about discontinuous functions. Also, we saw that for given a continuous function on a smaller set, how to extend that continuous function to a bigger set. Also, we saw that whether this continuous extension is unique or not, and under what condition it is unique, that also we have seen. And we have taken several examples to analyze these cases. Also, we have discussed various kinds of discontinuities, and by taking several examples, we have seen and we have classified this type of discontinuities also. And also, we have focused on a special types of function, that is actually monotonic functions, and we have discussed the discontinuities for these monotonic functions.
Yes.
And we also, through your puzzle, saw the power of the bisection method
Yes.
and how the change of base helped solve the problem. So
Yes.
And finally, we saw a simple example of a mathematical modeling problem where we calculated the number of messages received on the phone. So we use this linear approximation, f of t plus delta t is approximately equal to f of t plus delta t into f dash of t, and helps us in certain predictions.
Yes.
Excellent. We shall have more such explorations and expeditions in our future meetings.
Yes.
Sure,
See you.
sure.
Please call me whenever you have
Yeah,
discussions with the
yes.
students. I would love to join the discussions.
Yes.
Thank you.
Thank you very much.
Thank you,